Welcome to The Explainer. All right, today we are tackling a big one. It's one of the most powerful, but also one of the most feared concepts in all of programming. Yep, we're talking about recursion.
And hey, let's be real for a second. If just hearing the word recursion makes you a little nervous, you're in good company. I mean, it's a concept that trips up developers at pretty much every level, from beginners to seasoned pros.
But here's the thing, and this is super important. Getting over that hump, that fear, it isn't just a nice to have. It's absolutely critical if you really want to level up your programming skills.
I mean, think about it. If you don't really get recursion, you can't truly get data structures and algorithms. It's like a gatekeeper. Without it, you're basically locked out of some of the coolest, most powerful stuff. No trees, no backtracking, and no divide and conquer, no dynamic programming. It's kind of like you're coding with the training wheels still on.
So you know what? That's our mission for today. We're going to take those training wheels off. By the time we're done here, my promise to you is that recursion is going to feel logical. It's going to feel intuitive, not like some kind of confusing magic trick.
All right, so where do we start? Well, not with code. No, before we even look at a single line of code, we need to build a really solid, intuitive foundation. Let's start with a simple, real-world way to think about this whole thing.
Okay, so you look it up in a textbook and you get this. Recursion is a process where a function calls itself to solve smaller versions of the same problem. And yeah, that sounds kinda dry and abstract, right? So let's forget the textbook for a second and make this real.
Imagine this. You're standing at the bottom of a staircase, and you want to get to the 10th step. What's the very first thing you have to do to get there? Well, you have to get to step 9 first, right? And to get to step 9, you guessed it, you have to get to step 8. You see where this is going? Each big problem just breaks down into a slightly smaller, identical version of itself. That right there, that's recursive thinking in a nutshell. Now here's the secret sauce, the key to unlocking all of this. Every single recursive function, I don't care how complicated it looks on the surface, is built from the exact same two-part blueprint. Just 2 parts. So what are these 2 parts? First up, you've got the base case. This is your escape hatch, your emergency brake. It's the absolute smallest version of the problem that you can solve without any more recursion. Then you have the recursive case. This is the part that does the work of breaking things down. It's where the function calls itself, but, and this is key, with a slightly smaller problem, moving it one step closer to hitting that base case. And I cannot stress this enough. The base case is not optional. It's a matter of survival for your program. Forgetting it is like driving a car with no brakes. You just go on forever. Or in this case, until you cause what's called an infinite recursion. That leads to a Stack Overflow error, and boom, your whole program crashes. So rule number 1, always figure out your stopping point first.
Okay, so that's the theory. We've got the blueprint. Now let's see how this stuff actually works in practice. Let's peek under the hood and see what's happening in the computer's memory when a recursive function runs.
The magic behind all of this is a thing called the call stack, and the best way to picture it is literally like a stack of plates at a cafeteria. Every single time a function is called, your program puts a new plate on top of that stack. Easy enough, right?
Now this stack has one simple, unbreakable rule. LIFO, last in, first out. That means the very last plate you put on the stack is the very first one you have to take off. You can't reach down to the bottom. Just remember, last in, first out. All right, time for some code. Don't worry, it's a simple one. This is a recursive function that just prints numbers. See that if n equals 0 part? Boom, that's our base case, our stop sign. And that line right there, print n minus 1, well, that's our recursive case, the function calling itself. So let's trace this. What happens when we call print3? First, print3 gets put on the call stack, a new plate. But before it can do anything else, it calls print2, so another plate goes on top. Then print2 calls print1, another plate. And finally, print1 calls print0, one more plate. Now, when print0 gets called, it looks at that if statement and says, aha, n is 0. It hits the base case. The chain reaction stops right there.
Okay, so the calls have stopped. Now, the stack starts to unwind. Remember LIFO? Last in, first out. So print 0 was the last one in, so it's the first one to finish and get popped off the stack. Now, control goes back to print 1. It's finally free to do its work, which is to print 1. Then, it's done. Pop. Control goes to print 2. It prints 2. Pop. Finally, we're back to the original call, print 3. It prints 3, and we're all done. The final output on the screen, 1, 2, 3.
Okay, you ready for a quick pop quiz? Let's tweak the code a little.
What do you think happens if we take that print statement and move it before the recursive call? Just flip those two lines. Take a second. Think about that stack of plates and when the work gets done.
Did you guess it? The answer is 3, 2, 1. It completely reverses the output. Why? Because now each function does its printing first, and then it makes the next recursive call. So print 3 immediately prints 3, and then adds print 2 to the stack. This is a huge takeaway. Where you put the work in relation to the recursive call changes everything. It's not a small detail, it's fundamental.
Okay, so understanding the mechanics. The call stack, the base case, that's half the battle. But the other half, the really important part, is learning how to think recursively. How do you actually come up with these solutions on your own?
This brings us to what I believe is the single most important mental shift you can make. I like to call it recursive faith. What is it? It's the art of just trusting. You assume that your function will magically work for a smaller version of the problem, and you don't worry about how.
This means you have to actively change how you approach these problems. You have to stop trying to trace the whole thing in your head. Print 3 calls print 2 calls print 1. That'll just give you a headache. Instead, you take a leap of faith. You ask a much simpler question. Okay, let's just assume that my function fact of n-1 already works and gives me the right answer. How do I use that answer to find fact of n? See? You only have to solve for one single step. You trust recursion to handle all the other steps for you.
And why is this leap of faith so critical? Because it's the key that unlocks almost all of the advanced topics in data structures and algorithms. Things like traversing trees, backtracking algorithms, super efficient sorting methods like merge sort. They all suddenly click and become intuitive once you start thinking this way.
All right, let's wrap this up with a super quick recap. What did we learn? 1. Recursion is just a function that calls itself. 2. It absolutely must have a base case to know when to stop. 3. It's all powered by the call stack, which works on a last-in, first-out rule. And 4. The whole point is to break a big, scary problem down into smaller, manageable, identical pieces.
And I want to leave you with one last idea. If, after all this, recursion still feels a little fuzzy or a little confusing, good. Seriously, that's a great sign. It means your brain is forging new connections, learning a fundamentally new way to think. That feeling of discomfort isn't failure. It's the feeling of your brain getting stronger. It's the feeling of growth.